Level 1. The gravity you feel. Imagine lying in bed at night, still and silent. You feel something gently pulling you down the mattress, hugging back. That quiet pressure, it's gravity is the invisible pull between anything that has mass. It's why apples fall, why we stay grounded, why the dance is around the... But it's not just a... Einstein said it's a bend in the fabric of picture, stretching a bedsheet and placing a heavy ball in the center. Smaller objects roll toward it not because they're being grabbed, but because the space itself curves. Here's the simplest way to see it: drop a pen. It falls. That's gravity. A deeper version? The is falling too, just fast enough to keep missing the Earth. That's what an orbit really is. Gravity isn't loud or dramatic. It doesn't need to be. It's quietly holding everything together, from galaxies to your bones. People often think gravity just means falling down, but it's more than that. It's not. It shapes, it guides, it flows through everything. Want to recognize it? Notice how objects speed up as they fall. That's not magic. That's gravity doing what it's always done. And in those quiet moments, when everything feels scattered or out of place, just remember, it's still holding you close. Level 2. Why the sky is blue. You look up. The sky stretches wide, calm, endless, and blue. But have you ever asked, why not green or violet? The answer lies in how light dances through air. Sunlight looks white, but it's actually made of many colors, each with different wavelengths. When sunlight hits our atmosphere, it scatters. And here's the key: light scatters more than the rest. That's because it travels in shorter, tighter waves. So when the sun's rays strike air molecules, the blue spreads wide, painting the sky. But at sunrise and sunset, the sky turns orange or red. That's because the light has to travel farther, and the blue gets scattered away before it reaches you. What's left? The longer, warmer wavelengths. This isn't just science, it's a quiet reminder. Even the color of the sky is shaped by, and the blue you see, depends on where you stand. Many assume the sky is blue simply because of water or reflection. But it's deeper than that. It's physics, in motion, above your head. So next time you look up, you're not just seeing color. You're seeing scattered light from a prism. Level 3. The warmth of sunlight. You step outside, and the sunlight kisses your skin. It feels warm, almost personal, like the sky itself is reaching out. But how does that warmth travel across nearly 150 million kilometers of empty space? The answer lies in radiation, not the scary kind, but the gentle stream of energy that sunlight carries. Unlike sound or heat through touch, sunlight doesn't need air or matter to move. It rides in waves, electromagnetic waves. And when those waves hit your skin, they shake your molecules gently. That shaking, that's heat. That's why it feels warm, even though space between the sun and Earth is a cold, silent vacuum. The sun emits all kinds of waves: infrared, visible, ultraviolet. Some you feel, some you see, and some you don't even notice. But all of them carry energy wrapped in light. People often assume warmth means something is close, like a fire or a hand. But sunlight proves distance doesn't always mean disconnection. The heat you feel isn't from the air, it's from light, converted to motion in your atoms. So, next time you feel the sun on your face, pause. You're touching energy, born in the heart of a star. Level 4. How mirrors work. You glance into a mirror and see you, not reversed, not changed, just reflected. But how does a simple sheet of glass return an image so perfectly? The secret lies in how light bounces. Light travels in straight lines until it hits something. A mirror's surface is smooth, polished at the microscopic level. So when light strikes it, it doesn't scatter. It bounces back at the exact angle it arrived. That's called the LAW of reflection. If your nose faces the mirror, light from your nose hits the glass and bounces straight back to your eyes. You see yourself where the rays came from behind the glass, even though it's all happening right in front of you. Many think mirrors flip left and right, but they don't. They flip front to back. It's our brain that makes it feel reversed, like we're seeing someone else mimicking us. A mirror isn't magic. It's obedience, pure, predictable light behavior. So next time you look into one, remember, it's not just showing your face, it's showing how light honors the laws of nature. Straight in, straight out. A silent agreement between you and the photons. Level 5. The magic of magnets. You hold two magnets near each other. They snap together or push apart. No touch, no wires, just invisible forces. It feels like magic, but it's pure physics. Magnets work because of electrons, tiny, spinning, charged particles. In most materials, their spins cancel out, but in magnets, many of these spins line up, creating a magnetic field. That field reaches out, quietly influencing space. It attracts or repels, depending on how the poles face. North to south, they pull. North to north, they push, and the force weakens with distance, but it's always there. We use magnets everywhere, in speakers, motors, phones, even MRI machines. They guide compasses, lift trains, and store data on your hard drive. But what makes them feel so special is that they act without contact, a reminder that not all forces are visible. Some, like magnetism, work quietly behind the scenes. People often forget how essential they are, but magnets are one of the few forces that seem to cross the boundary between the seen and unseen. So next time a magnet snaps to your fridge, pause. You're holding a piece of orderly chaos, atomic alignment, made real. Level 6. Why ice floats? You drop an ice cube into a glass of water, and it floats calmly on top. Seems simple, right? But that gentle bobbing reveals one of nature's most beautiful quirks. Most substances get denser when they freeze, but water does the opposite. As it cools and approaches 0 degrees Celsius, its molecules start locking into a special structure, one that spreads them out. The result? Ice is less dense than liquid water, so it floats, and that small detail saves entire ecosystems. If ice sank, lakes and oceans would freeze from the bottom up. Life underwater would be crushed, frozen with no escape. But because ice floats, it forms an insulating layer on the surface, protecting what lies beneath. In a way, frozen water becomes a blanket. People often think floating just means lighter, but it's about density, mass relative to volume. Ice has more space between its molecules, which gives it buoyancy. So when you see an iceberg, remember, it's nature's clever exception, a rare case where freezing creates expansion, not contraction. And that quirk is the reason entire worlds stay alive beneath frozen surfaces. Level 7. How planes stay up? You sit in a plane, watching cities shrink below. It feels impossible, hundreds of tons floating in the sky. But flight isn't magic. It's balance, precision, and air. As the wings cut through the atmosphere, air moves faster over the top and slower underneath. Faster air means lower pressure. Slower air means higher pressure. That difference creates lift, a gentle upward push that counters gravity. It's called Bernoulli's principle, and it's the reason wings are curved on top. But lift alone doesn't keep a plane going. Engines push it forward, stabilizers keep it level, and ailerons adjust its direction. It's an orchestration, every part working together, fighting drag and weight. Planes don't defy physics, they use it, layer by layer. Many people think flying just means going fast, but speed without control doesn't lift anything. True flight comes from understanding air pressure, flow, and shape. So the next time you look out your plane window, take a breath. You're not just flying, you're riding invisible forces, engineered into harmony. Level 8. The push and pull of friction. Try sliding your hand across a table. You feel resistance, a kind of grip. That's friction, the invisible handshake between two surfaces. It slows things down, but it also lets us move forward. Friction happens because no surface is perfectly smooth. Zoom in close, and you'll see bumps, ridges, tiny mountains. When two surfaces meet, those microscopic edges catch, rub, and resist. That resistance creates heat, slows motion, and gives us traction. Without friction, you couldn't walk, write, or even sit upright. There are many types. Static friction holds things in place, while kinetic friction works once things start moving. Engineers have to balance it. Too much creates wear and waste. Too little, and you lose control. That's why cars need rubber tires, and machines need lubrication. People often blame friction for slowing progress, but it's also what makes progress possible. Without it, nothing could grip, climb, or stop. It's the subtle drag that gives us control, the quiet resistance that shapes every move. So next time something feels hard to push, remember, it's friction helping you stay grounded. Level 9. What causes rainbows? You step outside after a storm. The air is cool, the world is still, and there it is, a perfect arc of color hanging in the sky, a rainbow. But how does it form? The answer begins with sunlight and raindrops. Sunlight looks white, but it's made of many colors. When that light enters a raindrop, it slows down and bends, a process called refraction. Then, inside the drop, it reflects off the back and refracts again as it exits. During this journey, the light spreads into a spectrum: red, orange, yellow, green, blue, indigo, violet. Each color bends at a slightly different angle, creating the circular band we call a rainbow. The arc you see isn't in a fixed spot, it depends on your position relative to the sun and the raindrops. That's why no two people see exactly the same rainbow. It's not a thing in the sky. It's light returning just for you. Many think rainbows are rare or magical, but they're simply physics: light, water, and angle in harmony. So next time you catch one, don't chase it. Just stand still and let the light bend back toward you. Level 10. Sound waves in the night. You lie awake at night, windows open, a distant train passes, a dog barks far away. Everything feels quieter, yet somehow sounds seem sharper, closer. That's not your imagination. It's how sound waves move when the world slows down. Sound travels as waves through air, compressing and expanding the space between molecules. During the day, the sun heats the ground and creates turbulent air. That turbulence scatters sound, making distant noises fade. But at night, the air cools and settles into layers. Sound waves bend, or refract, back toward the ground instead of escaping upward. That's why you hear things more clearly after dark. This phenomenon is called temperature inversion. Warm air above, cool air below, and sound waves get trapped in the layer. It's like the atmosphere becomes a gentle hallway, guiding sound across long distances. People often think sound just travels straight, but it bends, reflects, fades, or even amplifies, depending on the world around it. So when night falls and your ears pick up distant echoes, pause. You're hearing more than noise. You're sensing pressure patterns stitched into the air, a reminder that even silence has layers. Level 11. Newton's first law. Motion never ends. You slide a book across a table, and it comes to a stop. But what if nothing was in its way? No surface, no friction, no air. Would it keep moving forever? According to Newton's first law, yes, it would. Motion, once started, doesn't end on its own. Also known as the LAW of inertia. This principle tells us that an object at rest stays at rest, and an object in motion stays in motion unless acted upon by an outside force. In space, where there's nearly no resistance, this law becomes more visible. Push something once, and it glides endlessly. On Earth, friction and gravity disguise this law. Everything seems to stop eventually, but that's only because something is pushing back. Remove those forces, and the motion continues forever. People often think things naturally slow down, but nature doesn't slow things without reason. Newton's first law reminds us that rest and motion are both natural states. So the next time you push a swing or toss a stone, remember you're watching a law that never quits. It's not resistance that keeps things going, it's the absence of it. Level 12. The pendulum's calm rhythm. Tick, tock, tick, tock. The slow sway of a pendulum feels hypnotic, calming, predictable. But beneath that rhythm is one of physics' most elegant truths. A pendulum swings because gravity pulls it downward, while inertia carries it forward. It converts potential energy at its peak into kinetic energy at the center and back again. This smooth exchange creates a motion that's surprisingly stable. The amazing part? A pendulum's period, the time it takes to swing back and forth, depends mostly on its length, not its weight. That's why old clocks could keep such perfect time, using nothing more than a swinging rod and a steady tick. People often assume heavier objects fall faster or swing harder, but the pendulum shows how nature values balance. It doesn't rush, it doesn't drift, it just moves in quiet repetition. Pendulums were once used to study the Earth's rotation and even earthquake patterns. They're more than timekeepers, they're truth tellers. So the next time you watch one move, pause. You're not just seeing motion, you're witnessing perfect compromise between pull and momentum. Level 13. Centripetal versus centrifugal force. Imagine swinging a bucket of water in a circle. The water stays inside, even when upside down. Why? Is something pulling it outward or inward? This is where physics gets tricky. The real force, keeping the bucket in circular motion, is centripetal. It pulls toward the center of the circle. It's the tension in your arm, constantly redirecting the bucket's path. Without it, the bucket would fly off in a straight line. But from the bucket's point of view, it feels like something's pushing it outward. That illusion is called centrifugal force, not a real force, but an effect of inertia in a rotating frame. It's your body swaying outward in a turning car. You're not being pushed. Your motion just wants to stay straight while the path curves. People confuse these two all the time, but understanding them helps explain how satellites orbit, how washing machines spin, or why roller coasters feel intense. So next time you're on a ride or swinging something fast, remember you're not being pushed out, you're being pulled in, and your body just doesn't like it. Level 14. Terminal velocity and falling forever. Imagine falling from a plane. At first, you accelerate faster and faster, but eventually, you stop speeding up. You're still falling, just not any faster. That's terminal velocity. When you fall, gravity pulls you down, but air pushes back. As you fall faster, the air resistance increases until it balances out the pull of gravity. That's the moment when acceleration stops and you fall at a constant speed. For a skydiver, around 200 kilometers per hour. Without air, you'd accelerate forever. But our atmosphere creates a natural speed limit. Even falling has boundaries. Many assume falling is just about going down, but it's really a tug of war between forces. Gravity says, go. Air says, wait. And terminal velocity is their truce. Understanding it helps engineers design parachutes, re-entry vehicles, and sports gear. It's not just about falling. It's about balance. The point where pushing stops helping. So if you've ever wondered how someone could fall calmly through the sky, it's because they've hit a peaceful speed. No faster, no slower. Just the sound of rushing air and gravity in quiet agreement. Level 15. Inertia, the lazy force. You're riding in a car. It stops suddenly, and your body lurches forward. That's inertia, the quiet tendency of things to keep doing what they're already doing. If something is still, it wants to stay still. If it's moving, it wants to keep moving. Not because it's thinking, but because of mass. The more mass something has, the more inertia it carries. That's why it's harder to push a boulder than a soccer ball. Inertia isn't a force, it's the absence of change. It resists acceleration, not because it fights you, but because it prefers consistency. It's nature's default setting. We feel inertia everywhere when lifting groceries, riding elevators, or tossing objects. And once you notice it, it's hard to unsee. It explains everything from why seatbelts are necessary to why planets keep orbiting. People often call it laziness, but it's deeper than that. Inertia is the universe's way of saying, stay the course. Change takes effort. Motion takes force. So, next time something resists being moved or keeps gliding longer than expected, you're watching inertia in action, the quiet anchor of all movement. Level 16. Levers and the power of balance. You've seen it on a playground, a seesaw, gently tilting back and forth. That's a lever in action, one of the oldest and simplest machines in physics. A tool that proves how power isn't always about strength, but position. A lever works by rotating around a central point called a fulcrum. On one side, you apply force. On the other side, the object moves. If the fulcrum is close to the object and farther from your hands, you need less force. That's mechanical advantage using distance to multiply effort. From crowbars to scissors, from wheelbarrows to bones in your body, levers are everywhere. They let us lift, pry, or balance things with grace. Not through brute force, but through clever arrangement. People often think effort means pushing harder, but levers teach us another truth. Sometimes it's about where you push. The right point can change everything. So next time you feel stuck, think of the seesaw. You don't always need more energy. You just need better leverage. Level 17. Action and reaction. Newton's third law. You jump off a boat and it drifts backward. You push a wall and feel it push you back. It's not resistance, it's balance. Newton's third law. For every action, there is an equal and opposite reaction. This law governs motion not just of rockets and machines, but your body every day. Push on the ground and it pushes back. That's how you walk. A bird flaps down, the air pushes it up. Nothing moves alone. When a rocket fires downward, hot gases shoot out, and the rocket lifts, not because it's pushing off the ground, but because it's pushing on the air itself. The force goes one way, the reaction sends it the other. People sometimes miss this symmetry. They see the push, but not the pushback. But Newton's third law reminds us forces come in pairs. No movement is isolated, so the next time you feel a push in life, pause. Somewhere, something is reacting always. Level 18. Angular momentum. Spinning secrets. A figure skater spins with arms outstretched, then pulls them in and spins faster. That's not magic, it's angular momentum, one of the most powerful and misunderstood ideas in motion. Angular momentum is the rotational version of regular momentum. When something spins, it wants to keep spinning unless something stops it. And the speed of that spin depends on how the mass is distributed. Pull it in tighter, you spin faster. Spread it out, you slow down. The Earth spins, tornadoes twist, neutron stars whirl at terrifying speeds, all because of angular momentum. It's conserved, meaning it doesn't disappear, just changes form. That's why a planet keeps rotating long after it formed. People often think only speed matters, but in spinning systems, it's more about distribution, the where of motion. So next time you watch a spinning top or toss a frisbee, remember, there's a quiet math behind that swirl. And if you ever feel out of balance, it might just be time to center your momentum. Level 19. Conservation of energy. Energy can't be created or destroyed, only transformed. That's the principle of conservation of energy. It's not just a rule. It's the backbone of how everything moves, heats, shines, and lives. When you stretch a spring, climb stairs, or charge a battery, you're storing energy. Let it go, and that energy turns into motion, heat, or light. It never vanishes. It just changes form. Chemical to kinetic, potential to thermal, always cycling. Even in a car crash, the energy of motion doesn't disappear. It spreads into sound, crumpled metal, heat. In physics, there's no such thing as gone, just converted, transferred, redistributed. People often think of energy as a thing, but it's more like a currency, exchanged, passed along, conserved. So the next time you flip a switch or toss a ball, remember, you're not creating energy, you're redirecting it. Everything you do is part of a larger flow. Level 20. Work, force, and energy explained. You push a box across the floor. You're applying force, but are you doing work? In physics, that word has a precise meaning, and it's all about movement. Work is done when a force moves something. Push hard, but it doesn't move, no work. Push gently, and it glides across the floor, that counts. The formula is simple. Work equals force times distance. The direction matters, only force in the direction of motion gets credit. And energy? That's the ability to do work. It powers the force. It moves the object. When you lift, heat, push, or pull, you're spending energy to get work done. People often confuse these terms, force, work, and energy. But think of it like this. Force is the push, energy is the budget, and work is the result. One sets things in motion, one pays the cost, one makes change happen. So, next time you're moving something, even yourself, remember, you're part of a system that turns effort into effect. Level 21. Refraction and the bending of reality. You dip a straw into a glass of water, and suddenly it looks bent, not broken, just misaligned, as if the world took a soft turn. That illusion is caused by refraction, the bending of light as it moves from one medium to another. Light slows down when it passes through something denser, like from air into water, and when its speed changes, its direction shifts. That shift creates the illusion of bending. It's not the straw that moves, it's the light itself. Refraction isn't just about straws or glasses. It's how lenses focus vision, how rainbows form, how stars appear to twinkle. It bends perception and reveals that reality isn't always where it looks. Even our atmosphere bends starlight, making the sun visible before it actually rises. Many assume what they see is what's real, but refraction is nature's way of reminding us light is not loyal to straight lines. It curves, shifts, bends around what it enters. So next time you see a warped image through water or glass, pause. You're not being fooled. You're being shown that reality itself is flexible. Level 22. How lenses shape sight. You hold up a magnifying glass, and suddenly letters grow bigger, details sharpen, things once blurry come into focus. That clarity isn't magic, it's lens, physics. Lenses work by bending light. As light enters or exits curved glass, it slows down and changes direction thanks to refraction. A convex lens, like in magnifiers or your eyes, brings light rays together. A concave lens spreads them apart. By shaping the path of light, lenses shape how we see. From eyeglasses to microscopes to telescopes, lenses help us explore the small, the distant, and the unseen. They adjust focus, correct vision, and reveal hidden worlds. And behind every lens is a careful balance of curve, thickness, and distance. People often take lenses for granted, small tools that sit on noses or cameras, but they're silent translators, turning scattered light into usable images. So, next time you adjust your glasses or zoom a camera, pause. You're not just seeing better, you're witnessing light being guided. Vision, focused by design. Level 23. The speed of light barrier. No matter how hard you push, no matter how much energy you add, nothing with mass can move faster than light. That's not a limit of technology. It's a limit of nature itself. The speed of light, roughly 300 kilometers per second, is the ultimate cosmic speed limit. As you accelerate closer to it, strange things begin to happen. Time slows down, mass increases, and energy demands skyrocket. Push harder, and the universe pushes back. Einstein's theory of relativity showed that the faster you go, the more warped reality becomes. End quote. Trying to reach light speed is like chasing a horizon that keeps moving away. You can get close, but never reach it. People often dream of faster-than-light travel, wormholes, warp drives, shortcuts. But physics, so far, holds the line. Light speed is a boundary between what's possible and what's fantasy. So next time you see a flashlight beam or sunlight in the morning, pause. You're witnessing nature's fastest messenger, a traveler that never rests and never goes any faster. Level 24. The Doppler effect in light and sound. A siren approaches, the pitch rises, it passes, and suddenly it drops. That shift, it's the Doppler effect. A wave's way of telling you something is moving. When a wave source moves toward you, its waves compress, making them shorter and higher in frequency. When it moves away, they stretch out longer, lower, softer. This works with sound and with light. For sound, it changes pitch. For light, it changes color. Stars moving toward us shift slightly blue, their waves compressed. Those moving away, they redden. This is how we measure the movement of galaxies without ever touching them. Many think waves just move outward, but the Doppler effect reveals a hidden layer motion embedded in vibration. So next time a train passes or a car hums by, notice the shift. You're hearing speed encoded in sound, and when you look up at the stars, you're seeing the same story in color. Level 25. Redshift and the expanding universe. When we look at distant galaxies, we notice something strange. Their light is redder than expected. That's not a color mistake. It's a message. A sign that the universe is expanding. As galaxies move away, their light waves stretch just like sound lowering as a car drives off. This stretching shifts the light toward the red end of the spectrum. It's called redshift. And it's how we know the universe isn't static. It's growing. In the 1920s, Edwin Hubble observed that the farther a galaxy is, the more redshifted its light. That means it's moving away faster. The space between galaxies isn't empty. It's stretching, like dots on an inflating balloon. Everything is drifting apart. People often imagine the universe as fixed, like a stage, but redshift tells us the stage itself is expanding, and we're riding it. So when you look at the night sky, you're not seeing stars in place. You're seeing ancient light stretched by the breath of space-time. Level 26. The illusion of time slowing down. You're standing on a platform, watching a train pass by. Inside, a clock ticks, but something feels off. To you, it ticks slower. To the passenger, it ticks normally. This isn't a trick, it's time dilation. As objects move faster, time slows down for them, relative to a stationary observer. This isn't just perception, it's measurable. It happens because of Einstein's theory of relativity. Time is not a fixed river. It flows differently depending on speed and gravity. At everyday speeds, you'd never notice. But at speeds close to light, seconds stretch. Atomic clocks flown on jets tick slower than those on Earth. And astronauts age just a little less than people here. People often think time is absolute, that it ticks forward the same for everyone. But time is deeply personal, tied to where you are and how fast you're moving. So the next time you feel like a moment stretched or a second disappeared, consider this. Time itself might have bent slightly, just for you. Level 27. The clock on the spaceship. Imagine a spaceship racing through space, close to the speed of light. Inside, a clock ticks steadily, but to someone watching from Earth, it ticks slower. This isn't malfunction, it's relativity in action. Einstein showed that time passes differently depending on motion. On that spaceship, time feels normal to the traveler, but to someone on Earth, it drags. Not because the clock's broken, but because time itself bends under motion. This isn't theory, it's tested. Scientists have flown atomic clocks around the planet and compared them to those on the ground. The airborne clocks ticked just a bit slower. The faster you go, the more time stretches. Many assume time is a universal constant, but this proves it's not. Time isn't a shared drumbeat. It's a rhythm that shifts with speed. So when we speak of the future or distance, we're really speaking about time, too. And if one day you leave Earth at high speed and come back, you might find the world has aged while you've barely changed, because your clock ticked differently in the silence of space. Level 28. Twin paradox. Two twins. One stays on Earth, the other boards a spaceship, travels near light speed, and returns. When they meet again, one has aged more. That's the twin paradox, and it's real. This thought experiment shows how time dilation works. The traveling twin, moving at high speed, experiences time more slowly. When they come back, they've aged less than their sibling, even though both started and ended together. It feels like a contradiction. Shouldn't motion be relative? Couldn't either twin say the other was moving? But here's the catch. The spacefaring twin accelerated and turned around. That breaks the symmetry. One experienced true motion, the other didn't. That's what makes the aging different. People often struggle with this idea that time can bend like that, but it's not a fantasy. We've confirmed it with particle decay rates, GPS satellite corrections, and precise atomic clocks. Time is elastic. So if you ever feel like time flies, maybe it does. And if you ever wanted to travel forward in time, you already can just move fast enough. Level 29. Time dilation. At high speeds, time slows down. Not just metaphorically, literally. This is time dilation, one of the strangest consequences of Einstein's theory of relativity. According to physics, time is not absolute. It stretches and shrinks based on speed and gravity. The faster you move, the more slowly your clock ticks compared to someone at rest. It's not just a theory, it's measured, verified, and baked into our GPS systems. Satellites orbiting Earth experience slightly different gravity and speed than we do on the ground. Their clocks must be adjusted constantly to stay in sync. Without that correction, your phone's location would drift by kilometers each day. People imagine time as a steady beat, but relativity reveals it as more like a flowing stream changing with terrain, speed, and force. And this isn't just about spaceships. Time dilation happens on mountaintops, in elevators, in every second we live. So next time you stare at the ticking hands of a clock, pause. It's not ticking the same for everyone. Somewhere out there, time is moving just a little bit differently. Level 30. Light as wave and particle. You turn on a lamp, and light pours out soft, steady. But what is it, really? A wave? A particle? The answer is both. Welcome to the dual nature of light. Light behaves like a wave. It reflects, refracts, interferes. It has a wavelength, a frequency, a rhythm, but it also behaves like a particle. Photons, tiny packets of energy, arrive one by one, carrying discrete amounts of force. This baffled scientists for years. Waves shouldn't show up as particles. Particles shouldn't interfere like waves. Yet light does both, depending on how you look. Shine it through two slits, and you'll get an interference pattern. Measure it directly, you'll find individual photons. This duality isn't just about light. It's a principle at the heart of quantum mechanics, that the world can behave in contradictory ways. That how you measure something changes what you see. So the next time light flickers on your wall, or glows through the clouds, remember, you're not just seeing brightness, you're witnessing a paradox made real. One thing, behaving like two. Level 31. Entropy, the universe's tendency to mess. You clean your room. A day later, it's messy again. That's not laziness, that's entropy. The universe naturally moves from order to disorder. In physics, entropy measures how spread out or disorganized energy is. A tidy room has low entropy, a messy one, high entropy. Over time, systems tend to become more random. It's not a flaw, it's a rule. The second law of thermodynamics guarantees it. Left alone, energy disperses. Heat moves from hot to cold. Buildings decay. Stars burn out. Entropy always increases or stays the same. That's why you can mix cream into coffee, but not unmix it. Why you can break a glass, but can't make it whole again. People often mistake entropy for chaos, but it's not evil, it's inevitable. It shows us time's direction, a universal clock that never ticks backward. So next time things feel like they're falling apart, remember, in a way, they're just following nature's deepest rhythm. Level 32. Absolute zero. Imagine a place where all motion stops. No shaking atoms, no heat, no sound. That's absolute zero, the coldest temperature possible. 0 Kelvin. Not cold, but the absence of energy. At absolute zero, particles reach their lowest energy state. They don't move, they don't vibrate. It's not just cold, it's stillness. A deep, unreachable silence in the universe. We've gotten close just billionths of a degree above it, but we've never truly reached it. That's because, as you cool something, removing more and more energy becomes harder. The closer you get to zero, the more energy it takes to keep going. People often confuse low temperature with absolute zero. But this point isn't just another degree, it's the end of thermal motion, the flaw of physics. So next time you touch something freezing, remember, it's cold, but still a long, long way from stillness. Level 33. Heat death of the universe. Imagine the future far beyond stars, beyond galaxies, beyond time as we know it. A universe cold, dark, and still. That's the heat death, the quiet final act of cosmic thermodynamics. As entropy increases, energy spreads out. Stars burn their fuel, black holes evaporate, galaxies drift apart. Eventually, everything reaches equilibrium. No temperature differences, no usable energy, no more reactions, just stillness. It's not an explosion or collapse. It's more like fading, a slow, inevitable slide into uniformity, where nothing changes because everything is the same. People often imagine the end as dramatic, but physics paints a softer picture, not destruction, but exhaustion. So when you look up at the stars, remember, they're burning now, but not forever. Someday, the universe will grow quiet, not in sadness, but in balance. Level 34. The arrow of time. Crack an egg, and it shatters, but have you ever seen it uncrack? That's the arrow of time, the one-way flow from past to future. Time, in physics, is strange. Most laws are reversible. Equations work forward or backward, but in real life, things happen one way. You remember yesterday, not tomorrow. That's because entropy disorder always increases. As systems move from order to chaos, time moves forward, not because clocks say so, but because of probability. It's more likely for things to become messy than to spontaneously arrange themselves. That's what gives time its direction. People often ask why time only goes one way, but it might be better to ask, why does disorder rise? That's the real reason we age, forget, and never go back. So next time you watch something fall apart, know this: it's not failure, it's the universe, gently reminding you that time flows through change. Level 35. The first law of thermodynamics. Energy doesn't vanish. It doesn't appear out of nowhere. It only changes form. That's the first law of thermodynamics. The principle of energy conservation. Whether it's light becoming heat or food turning into motion energy is never lost. It shifts. It transfers. In every closed system, the total amount stays constant. Burn fuel. Energy becomes light, sound, warmth. Ride a bike, your muscles power motion and heat. This law anchors physics. Without it, nothing would make sense. No engines, no stars, no biology. Every machine, every living thing runs on transformations, not creation. People often say they're out of energy, but really, that energy just moved into heat, into sound, into the world around you. So next time you light a candle or feel warmth from your laptop, pause. That's energy, changing costumes, never lost, always present. Level 36. The second law, no free lunch. You can't turn all your food into motion. You can't make a machine that runs forever without energy. Why? Because of the second law of thermodynamics. It says, entropy always increases, and that means energy always loses usefulness. In any energy exchange, some of it becomes less usable, often lost as heat. A car engine, a boiling kettle, even your own body, they all leak energy into the environment. You can't get 100% efficiency. There's always a little waste. This law rules out perfect machines and infinite loops. It draws the boundary between fantasy and reality. It's why no process can be completely reversible. Every action has a cost. People sometimes hope to beat the system to build something that gives more than it takes. But the second law reminds us, energy comes with conditions. So the next time you flip a switch or heat a pan, know this: you're spending energy and losing a little every time. Because in this universe, there's no such thing as a free lunch. Level 37. Maxwell's Demon. Imagine a tiny being perched between two rooms, one filled with fast particles, the other with slow ones. The demon opens and closes a door, letting only fast particles into one side. Eventually, one room gets hotter and the other colder. Without using energy, that's Maxwell's Demon, a thought experiment that challenges the second law of thermodynamics. If such a demon existed, it could lower entropy without doing work. It would create order from chaos, a violation of nature's rules. But there's a catch. Observing and deciding requires information, and processing that information requires energy. In the end, the demon isn't free. Its choices come at a cost, and when you add that cost to the system, entropy still increases. The second law stands. People often use Maxwell's demon to explore the edge of physics, where information meets energy. It shows us how even a tiny, imaginary creature can reveal deep truths about how our world works. So next time you think of hacking the system or skipping steps, remember, even the demon pays. Level 38. Perpetual motion machines. A machine that runs forever. No fuel, no input, no friction, just motion without end. It's a dream as old as physics, the perpetual motion machine. But it's a dream that breaks the rules. The first law says energy can't be created. The second says you'll always lose some to heat, friction, or noise. Put them together, and perpetual motion becomes impossible. No matter how clever the design, the universe keeps the receipt. Inventors have tried spinning wheels, magnetic motors, sealed systems, but every one of them breaks down, slows down, or relies on hidden inputs. Because even the best machines leak energy somewhere. People want free power, a system that gives more than it takes. But physics is clear. Every system pays a toll. So next time you hear about a device that powers itself forever, smile, but stay skeptical. Because if perpetual motion were real, it would rewrite the laws of nature, and so far, those laws haven't budged. Level 39. Carnot engine and efficiency limits. Every engine loses some energy, but how much is the best it can possibly do? That's what the Carnot engine helps us understand, the theoretical gold standard of efficiency. Named after Sadi Carnot, this ideal engine operates between two temperatures, a hot source and a cold sink. The bigger the temperature difference, the more work you can extract. But even in a perfect, frictionless world, it can't be 100% efficient, because some energy always escapes. The Carnot efficiency sets a ceiling, a limit that no engine can exceed. Not your car, not a steam turbine, not even your body. It's a law that defines how good can get. People often ask, why not build a perfect machine? But perfection isn't just hard, it's forbidden. The Carnot engine reminds us that limits aren't flaws, they're frameworks. So next time you feel frustrated by waste or heat, remember you're already dancing at the edge of what's possible. Level 40. Thermal equilibrium. Touch a cold spoon with a warm hand, and you'll feel the chill. But wait a moment, and they match. That's thermal equilibrium, the quiet handshake between objects. When two bodies at different temperatures touch, heat flows from the warmer to the cooler until both reach the same temperature. At that point, the flow stops. Not because there's no more energy, but because there's no difference left. This principle governs everything from weather systems to engine design. It's why thermometers work, why food cools, why your blanket keeps you warm. Heat always seeks balance. People often think of equilibrium as stillness, but it's actually the result of motion, countless particles colliding, sharing energy, finding common ground. So next time you warm your hands by a cup of tea, pause. You're not just heating up. You're entering quiet agreement with the universe's love of balance. Level 41. Standing waves. Pluck a guitar string and it vibrates, but not chaotically. It forms patterns, frozen shapes that seem to shimmer in place. These are standing waves, vibrations that reflect, bounce, and interfere in just the right way. Unlike a moving wave, a standing wave doesn't go anywhere. It stays in place, with nodes that don't move and antinodes that pulse up and down. It forms when a wave reflects off a boundary and perfectly overlaps with its incoming self. The result? A stable, repeating rhythm locked into space. You see them on strings, in pipes, and even in microwave ovens. Wherever waves can echo and interact, they can stand. It's how musical instruments sing in tune, and why every object has a natural frequency. People often think waves are always moving forward, but standing waves remind us sometimes motion becomes pattern. So the next time you hear a pure note or see a ripple pause, you're witnessing energy at rest, dancing in place. Level 42. Harmonics in music and matter. Play a note on a violin, and you don't just hear one sound, you hear many. Hidden within that tone are harmonics, layered waves that give sound its richness. A string doesn't just vibrate at one frequency. It vibrates at multiples half the length, a third, a quarter. Each of these vibrations creates a harmonic. The first harmonic is the fundamental tone. The others add color, shape, and emotion to the sound. But harmonics aren't just musical. They exist in buildings, bridges, even atoms. Anything that vibrates can produce a harmonic series. Engineers study them to make structures stronger. Musicians use them to tune and blend. People often think of sound as one note, one pitch, but it's a tapestry of vibrations woven together. So next time you hear a cello or a flute, pause. You're not just hearing a note, you're hearing a fingerprint, a spectrum of resonating possibilities. Level 43. Resonance. The Tacoma Bridge Fall. In 1940, a bridge in Washington swayed gently in the wind. Then it twisted, danced, and collapsed. All because of resonance, a powerful force hidden in repetition. Resonance happens when an object is exposed to regular vibrations at its natural frequency, like pushing a child on a swing, timed just right. Each push adds energy. Eventually, the motion grows wild. For the Tacoma Narrows Bridge, the wind didn't push hard, it pushed perfectly, matching the bridge's own rhythm. The result? Oscillations grew until the structure tore itself apart. Resonance isn't always destructive. It's what makes a wine glass sing, or why a violin vibrates beautifully. But left unchecked, it can be dangerous. End quote. People often think strength is about mass or size, but resonance teaches us that timing matters. A small, regular force, in sync, can move the immovable. So, next time something sways in rhythm, remember it's not just moving, it might be resonating. Level 44. Interference. When waves collide, drop two stones in a pond and watch their ripples meet. Sometimes they build up, sometimes they cancel out. That's interference, the strange math of overlapping waves. When two waves meet, they combine. If their peaks align, the result is stronger, constructive interference. If a peak meets a valley, they weaken or cancel out, destructive interference. It's not magic, it's how waveforms add together in real time. This happens in sound, light, water, even quantum particles. Noise-canceling headphones, interference. Rainbow-colored oil slicks, also interference. People often assume waves pass through each other untouched, but in reality, they interact, creating new patterns, even silence. So next time two sounds blend, or two lights shimmer strangely, you're witnessing not conflict, but combination. Waves working together or against each other. Level 45. Beats and wave superposition. Play two notes, slightly out of tune, and you'll hear a slow pulse, a rise and fall in volume. That's a beat created by superposition. When two similar frequencies overlap, their waves interfere. Sometimes they add up, sometimes they cancel out. This creates a rhythmic pulsing, not from any instrument, but from the difference between the notes. The closer the frequencies, the slower the beat. Farther apart, the beat speeds up or disappears. Beats are useful. Musicians use them to tune instruments. Scientists use them to measure tiny differences in sound, light, or motion. It's a precise effect born from simple wave math. People often think sound is steady, but beats reveal that even stability can hold surprises. So, next time you hear a warbling tone or a slow flutter in music, pause. You're listening to two voices in close conversation, disagreeing, just enough to be beautiful. Level 46. Diffraction, the bending around. Shine a light through a tiny slit, and it doesn't just pass through, it spreads, bends, softens at the edges. That's diffraction, the way waves curve around corners. When a wave, sound, light, or water hits an obstacle or slit about its own size, it doesn't just stop or reflect. It bends around, creating patterns of light and dark, or sound and silence. It reveals that waves don't need a straight path. They adapt. You see diffraction in everyday things. The rainbow shimmer on a CD, the glow around a street lamp in fog, the softness in shadows, even your ability to hear someone around a corner. That's sound diffracting. People often think of light as laser straight, but diffraction reminds us waves are flexible. They bend around, fill space, and create beauty from limitation. So next time you see a fuzzy edge or glowing halo, pause. You're watching light breathe around barriers. Level 47. Polarization of light. Light looks soft and uniform, but it's not. It vibrates, and that vibration can be controlled. That's polarization, the filtering of light's direction. Unpolarized light vibrates in all directions, but when it passes through certain filters, like polarized sunglasses or reflective surfaces, only one direction remains: horizontal. Vertical, diagonal, that filtered light is polarized. This helps us reduce glare, read LCD screens, and even study the cosmos. Polarized light tells scientists about magnetic fields, dust clouds, and the surfaces of distant planets. People think light is just brightness and color, but polarization adds a hidden layer, a silent alignment. So next time you tilt your phone or wear sunglasses on a sunny day, remember you're not just blocking glare, you're dancing with light's direction. Level 48. Wave-particle duality. Is light a wave or a particle? The answer is both, and that's one of the strangest truths in all of physics. Light behaves like a wave. It bends, reflects, and interferes, but it also arrives in tiny packets called photons, energy particles with no mass, traveling at light speed. And it's not just light. Electrons too can behave like waves. This duality means that what we see depends on how we measure. Shine light through slits, it creates interference, like a wave. Detect it on a screen, you get individual dots like particles. Same system, different view. People often want clear categories. Something is either this or that. But wave-particle duality tells us that nature is more flexible. So next time someone asks, is it one or the other? Remember, sometimes it's both. Level 49. Quantum tunneling. Imagine throwing a ball at a wall, and it appears on the other side. No break, no hole, just through. That's quantum tunneling. A particle slipping past a barrier it shouldn't cross. In classical physics, if something doesn't have enough energy to climb over a hill, it stays put. But in quantum mechanics, particles aren't just points, they're probability waves. And part of that wave might exist on the other side of the barrier. So sometimes it just shows up there. This isn't just theory. It happens in real life, inside the sun, during radioactive decay, in the tiny circuits of your computer. Tunneling powers the quantum world. People often imagine walls as solid, final, but at the quantum level, certainty melts. What can't happen sometimes does. So next time you think something's impossible, remember particles tunnel. They don't always take the door. Level 50. The double slit experiment. Take a beam of light, shine it through two narrow slits. What you expect are two bright lines on a wall, but what you get is an interference pattern. Light acting like a wave. Then you try the same with electrons. One at a time, they still make the same pattern, like each particle interferes with itself. Until you watch, the moment you observe which slit it goes through, the pattern vanishes, the electron picks a side. This is the double-slit experiment, the heart of quantum weirdness. It shows that particles behave like waves until measured. Then they behave like particles. People often say, seeing is believing, but this experiment shows that seeing changes what is. That observation shapes outcome. So next time you wonder if attention matters, remember the slits, where watching changes reality. Level 51. Heisenberg's uncertainty principle. In the quantum world, certainty fades. You can know where a particle is, or how fast it's moving, but not both, not exactly. That's Heisenberg's uncertainty principle. At microscopic scales, particles behave like waves, and measuring one part of that wave, its position disturbs the other, its momentum. The more precisely you know one, the fuzzier the other becomes. It's not a flaw in your tools. It's a fundamental property of reality. This principle doesn't stop things from existing. It just sets a limit on how well we can predict them. Electrons don't have fixed paths. They exist in clouds of possibility, guided by probability, not precision. People often crave certainty. We want to measure, define, lock things into place. But the uncertainty principle reminds us the universe is softer than we think. So next time you can't pin something down, remember, even nature leaves room for mystery. Level 52. Schrödinger's cat. A cat in a box. Alongside it, a tiny particle waiting to decay. If it decays, poison is released. If not, the cat lives. But until you open the box, the cat is both alive and dead. That's Schrödinger's cat, a thought experiment, not a real one, meant to expose how strange quantum physics truly is. In the quantum world, particles exist in superpositions, multiple states at once, but when you measure them, they collapse into one outcome. Schrödinger's cat takes this idea to the extreme, tying a quantum event to something familiar. The point isn't about the cat, it's about measurement. When does a possibility become reality? Is it when we look, or before? Does observation create truth? People often laugh at the idea of a half-dead cat, but this paradox points to a deeper truth that quantum states are delicate, undefined, dependent. So next time you make a decision, or peek at a result, pause. You might be the observer, collapsing a possibility into what is. Level 53. Quantum entanglement. Two particles meet and become linked. No matter how far apart they drift, a change in one instantly affects the other. That's quantum entanglement. Einstein called it spooky action at a distance, but it's real and it's been proven. Entangled particles share a single quantum state. Measure one, and you instantly know the state of the other, even across galaxies. It doesn't send a signal. It just knows, not because of communication, but because their states are fundamentally connected. This isn't telepathy or magic. It's a deep mathematical relationship. Entanglement powers quantum computers, encryption, and new forms of information sharing. People often think of separation as distance, but entanglement reminds us connection can exist beyond space. A shared origin can ripple through the universe. So next time you feel distant from someone or something, remember, some bonds aren't broken by space, only deepened by it. Level 54. Quantum decoherence. In the lab, a particle behaves like a ghost in two states at once. But step outside, and things become ordinary again. Why? Because of quantum decoherence, the reason why superpositions don't last forever. Decoherence happens when a quantum system interacts with its environment. Heat, light, air molecules, they all disturb the delicate balance. The wave function collapses, and the system becomes classical, no more strange overlaps, just one defined outcome. This isn't observation, it's interaction. The universe isn't watching, it's bumping into things. And in those bumps, quantum weirdness fades. People think the quantum world is far away, but decoherence happens constantly inside your phone, in your eyes, in your body. The strangeness is there, but the noise of the world drowns it out. So next time you wonder why reality feels stable, remember, it's not absence of magic, it's a flood of interactions, smoothing it away. Level 55. The observer effect. You flip a light switch, the bulb glows, but in the quantum world, just the act of looking changes everything. That's the observer effect, not psychological, but physical. In quantum systems, particles exist in uncertain states, but when you measure them, observe them, the state collapses into something definite. It's not that you're interfering, it's that the system can't be measured without being touched. No observation is neutral. This effect shows up in experiments where particles behave differently when measured. The double slit setup is one example where watching the slits destroys the interference pattern. It's as if reality reacts to attention. People think of science as objective, but in quantum physics, the line between watcher and watched blurs. So next time you observe something in nature, in others, or in yourself, remember, even the act of watching has power. Level 56. Superposition. Many states at once. Imagine flipping a coin, and until it lands, it's both heads and tails. That's the strange heart of superposition. A quantum system can exist in multiple states until it's measured. An electron isn't just here or there. It's in a cloud of possibilities, a wave function that includes every outcome at once. Until we look, those outcomes coexist. But the moment we measure, the wave collapses. One result becomes real. This idea explains interference patterns, quantum computing, and even the weirdness behind Schrödinger's cat. It's not that the particle doesn't know what it is, it's that it is all things simultaneously. People want reality to be fixed, one answer, one outcome, but superposition reminds us, sometimes, truth is layered. So next time you're waiting for clarity, remember, multiple possibilities might still be alive until you choose. Level 57. Planck's constant and quantization. In 1900, Max Planck made a bold proposal that energy isn't continuous. It comes in quanta, tiny, indivisible chunks. And the size of those chunks, defined by Planck's constant. This tiny number, about 6.626 x 10⁻⁴, became the foundation of quantum mechanics. It tells us how much energy a photon carries based on its frequency. No in-between, no fractions, just packets. Planck's constant set the scale for the quantum world. It explains why atoms don't collapse, why electrons stay in shells, and why light has a particle-like nature. It turned physics into something pixelated, where energy comes in steps, not streams. People often imagine energy like flowing water, but Planck showed us it's more like bricks built in units you can't split. So next time you turn on a light or heat your tea, remember the warmth and brightness arrive one packet at a time. Level 58. Probability fields. Where is the electron? The answer isn't a point, it's a probability field, a cloud of chances, a map of maybes. In quantum mechanics, particles aren't locked in place. Instead, they exist in wave functions, mathematical descriptions of all the places they might be. These wave functions form probability fields. The denser the cloud, the more likely you'll find a particle there. But until you measure, it's not just unknown, it's undefined. There's no true position, just likelihood. The act of observing turns probability into location. People want certainty to know where things are, but quantum physics teaches us that reality isn't fixed until we look. So next time you search for clarity, pause. You might be asking the wrong question, because sometimes things aren't lost, they're just fuzzy by design. Level 59. Spin and quantum identity. Particles spin, not like planets but in a quantum way. They have spin, a built-in form of angular momentum that defines how they interact, align, and combine. But you can't see it spin, you can only measure its effects. Electrons have a spin of 1/2, photons have a spin of 1. These values aren't speeds, they're identities. They affect how particles behave in magnetic fields, how they bond into atoms, how they follow rules like the Pauli exclusion principle. Spin is why electrons fill shells in atoms, why matter has structure, why some particles obey symmetry, while others don't. It's not motion, it's a quantum label. People often assume particles are simple dots, but spin adds richness, direction, polarity, character. So next time you hear the word spin, think deeper. You're not just learning about rotation, you're learning what makes a particle itself. Level 60. Bell's theorem. In the 1960s, physicist John Bell asked a question: can quantum entanglement be explained by hidden variables? His answer rewrote the rules. That's Bell's theorem. Bell showed that no local theory where effects have nearby causes can explain the predictions of quantum mechanics. When particles are entangled, their behavior violates something called Bell's inequality. This means one particle's measurement instantly affects the other, no matter the distance. Experiments confirm this again and again. Quantum mechanics doesn't just look spooky, it is. The universe isn't locally determined, it's globally connected. People often assume reality is built from parts, tiny bits, following tiny rules. But Bell's theorem shows that nature might be more like a web, where threads pull across vast distances. So next time you wonder whether everything is truly separate, remember, physics may already be whispering, no. Level 61. The Big Bang. Imagine the entire universe compressed into something smaller than a grain of sand. No stars, no space, no time. Then, a rapid expansion. Not an explosion outward, but space itself, growing. That's the Big Bang, the beginning of everything we know. Roughly 13.8 billion years ago, The universe began expanding from a single point. It wasn't a blast into empty space. Space itself was being created. Time started ticking. Light began moving. Matter cooled and clustered into stars, galaxies, and worlds. We still see the echo of that moment, the pattern in the stars, the distant glow of ancient light. The Big Bang wasn't loud, it was quiet, cosmic, unfolding. People often imagine it as chaos, but it was structured, governed by laws. So next time you look at the night sky, remember, everything began not with noise, but with expansion. The universe didn't just begin, it continues, even now. Level 62. Cosmic microwave background. Turn on an old TV, and you might see static. A tiny part of that noise is something ancient, the cosmic microwave background. The afterglow of the Big Bang, roughly 380 years after the universe began, it had cooled enough for atoms to form. Light, once trapped by plasma, could finally move freely. That light still travels today, stretched into microwave radiation by billions of years of expansion. We've mapped this faint glow, and it's almost perfectly uniform with tiny ripples that became galaxies. It's the earliest picture of our universe. Not of stars or planets, but of space, becoming. People often think space is empty, but the cosmic background proves it remembers. Even now, every direction holds a whisper of creation. So next time you sit in silence, know this: the universe still hums with its first breath. Level 63. Inflation theory. Right after the Big Bang, the universe didn't expand slowly. It inflated faster than the speed of light. In a fraction of a second, everything grew unimaginably large. That's the core of inflation theory. Inflation helps explain why the universe looks so uniform, even in regions too far apart to have ever interacted. It also accounts for the tiny quantum ripples that grew into galaxies and clusters. This wasn't just expansion, it was exponential stretching of space itself. A balloon growing faster than light could cross it. Then, just as suddenly, inflation stopped and slower expansion took over. People often ask how the universe became so smooth, so flat, so balanced. Inflation offers an answer not by chance, but by stretching. So next time you think change takes time, remember, some of the biggest changes happen faster than light. Level 64. Multiverse hypothesis. What if this universe is just one of many, countless realities, each with its own laws, timelines, and stories? That's the multiverse hypothesis, an idea that stretches our imagination. In some versions, each quantum decision creates a new branch, a new universe. In others, inflation continues endlessly, spawning bubble universes with different physics. Ours might be just one room in an infinite mansion. We can't observe these other universes, not yet, but their existence could explain strange coincidences, why our universe seems so finely tuned for life. Maybe we live in one of the few where life can exist. People often want one reality, one truth, but the multiverse suggests a broader canvas. So next time you wonder, what if things had gone differently? Remember, in some universe, maybe they did. Level 65. The shape of the universe. Is space flat, curved, infinite? The shape of the universe isn't just a geometry question, it's about the fate of everything. If space is flat, parallel lines stay parallel, and the universe expands forever. If it's positively curved like a sphere, it could loop back on itself. If negatively curved like a saddle, it might stretch endlessly, but strangely. Astronomers study the cosmic microwave background, galaxy clusters, and the way light bends to infer shape. And so far, the evidence points to a universe that's remarkably flat, with just a hint of mystery. People often think space has edges like a box, but the shape of the universe may be boundless, yet finite. So next time you look up, don't just ask, how far? Ask, what shape is the everything I'm standing in? Level 66. Hubble's Law. In the 1920s, Edwin Hubble made a quiet discovery. Galaxies are moving away from us, and the farther they are, the faster they move. That became Hubble's Law. This law revealed something profound. The universe isn't static, it's expanding. Light from distant galaxies stretches, shifting toward red. This redshift is like a cosmic speedometer, showing us that space itself is growing. The relationship is simple: double the distance, double the speed. That means everything isn't flying away from a center. Space is stretching between everything. People often imagine the universe as an explosion, but Hubble's law shows us it's not things moving through space, it's space expanding with them. So next time you wonder how big the universe is, remember it's not just big, it's getting bigger. Level 67. Dark matter. Galaxies spin too fast. Stars at the edges move as quickly as those near the center, but visible matter alone can't account for this. Something unseen must be holding it together. That something is dark matter. It doesn't emit light, absorb radiation, or reflect anything we can detect directly, but its gravitational pull is undeniable. It surrounds galaxies in vast halos, shapes clusters, and bends light across space. We've never seen a dark matter particle, but we've mapped its presence, not by sight, but by effect. It's the ghost scaffolding of the cosmos. People often say, seeing is believing, but dark matter reminds us the most important forces may be invisible. So next time you look into the night sky, know that the stars aren't alone. They're dancing in the grip of something silent. Level 68. Dark energy. In the late 1990s, astronomers found something surprising. The universe isn't just expanding, it's accelerating. Some unknown force is pushing galaxies apart faster and faster. That force is called dark energy. Unlike dark matter, which pulls things together, dark energy pushes outward. It's smooth, uniform, and fills space itself. The more space expands, the more dark energy there is to drive expansion further. It now makes up about 70% of the universe, and yet we know almost nothing about it. No particles, no signals. Just the eerie fact that it's winning, slowly tearing the cosmos apart. People often think emptiness is nothing, but dark energy shows us that even nothing has power. So next time you consider what's in the void, know that it may be the most powerful force in the universe. Level 69. The observable universe. Look in any direction, and light travels back to you from stars, galaxies, and deep time. But there's a limit, a horizon. That's the edge of the observable universe. Because light travels at a finite speed, and the universe has a finite age, we can only see so far, about 46 billion light-years in any direction. Beyond that, light hasn't had time to reach us. But that boundary isn't fixed. It grows as the universe ages. And beyond it, maybe more galaxies, maybe nothing. We simply don't know, not because it's hidden, but because it hasn't arrived yet. People often ask, how big is the universe? But the better question is, how far can we see? So next time you gaze at the stars, remember you're looking into the deepest past, limited only by time itself. Level 70. The end of the cosmos. Will the universe end in fire, in ice, or just drift into silence? Scientists have explored many scenarios, but one stands out: the slow, inevitable fading of everything. As dark energy drives expansion, galaxies move farther apart, stars burn out, black holes evaporate. Eventually, even atoms may decay. This is called the heat death, not because of heat, but the absence of difference. No gradients, no reactions, just stillness. Other ideas exist: a big crunch, a big rip, quantum rebirth. But all agree, the cosmos, like all things, changes. And someday, perhaps, it will become something else. People often imagine endings as sudden, but the end of the universe may be quiet. So next time you think of forever, consider this: even forever evolves. Level 71. Special relativity. In 1905, Einstein proposed something bold: that the laws of physics are the same for all observers, and the speed of light never changes. From that came special relativity, a theory that rewrote space and time. When objects move close to light speed, time slows for them. Distances shrink, mass increases. These aren't illusions, they're real, measurable effects. The faster you go, the stranger the universe behaves. It's not just about speed, it's about perspective. What's true for one observer might not be for another, and yet, both are right. People often think time and space are fixed, absolute, but special relativity shows they're flexible, woven into motion. So next time you feel the world speeding up, remember, maybe time is stretching just for you. Level 72. General relativity. 10 years after special relativity, Einstein took things further. He introduced general relativity, a theory of gravity, not as force, but as geometry, space and time, curved by mass. According to general relativity, objects follow the curves of space-time. Planets orbit stars, not because they're pulled, but because they're moving along bent paths. Even light, massless and fast, bends near massive bodies. This theory predicted black holes, time dilation near gravity wells, and the bending of starlight. Every test from GPS satellites to colliding stars has confirmed it. People used to see gravity as a simple pull, but general relativity reveals it as deeper, a gentle warping of the universe itself. So next time you drop something or watch a planet rise, remember, you're seeing the shape of space, guiding motion. Level 73. Space-time curvature. Think of a trampoline with a bowling ball in the center. Drop a marble nearby, and it rolls toward the ball not because it's pulled, but because the surface is curved. That's space-time curvature. Mass bends space. Time bends too. Together, they form a four-dimensional fabric, and objects move through that fabric, following its curves. That's what we call gravity. The more massive an object, the deeper the bend. A star warps space gently. A black hole warps it violently. Even Earth creates curves, and we feel them every day. People often imagine space as empty and flat, but space-time is active, responsive, shaped by every star, every planet, every step. So next time you feel your weight, remember, you're not being pulled. You're moving through a universe that curves. Level 74. Gravitational waves. When two massive objects collide like black holes or neutron stars, they send ripples through space itself. Not sound, not light, but waves of gravity. These are gravitational waves. Einstein predicted them in 1916, but we didn't detect them until 100 years later. In 2015, LIGO, a massive observatory with laser arms, 4 kilometers long, recorded the tiny tremor of a black hole merger, a ripple in space-time, felt on Earth. These waves are faint but powerful. They carry stories of collisions billions of years old. They move at the speed of light, stretching and squeezing space as they pass. People often think gravity is still a background force, but gravitational waves reveal it can move, vibrate, echo. So next time the world feels quiet, remember, the universe might be singing. Level 75. Black holes. A star dies and collapses. Its mass shrinks into a single point. No light escapes. No information returns. That's a black hole, the most mysterious object in the cosmos. Black holes don't suck things in. They curve space-time so sharply that falling in becomes inevitable. Cross the event horizon, and escape becomes impossible, not because you're pulled, but because space itself leads only inward. At their center is a singularity, a point of infinite density. Around them, accretion disks swirl and glow. Some spin, some merge, some tear stars apart. All of them warp time and space beyond comprehension. People often see black holes as voids, but they're also engines shaping galaxies, bending light, storing secrets. So next time you look into darkness, remember, it might be holding more than silence. Level 76. White holes. Imagine the opposite of a black hole, not a place where nothing escapes, but one where nothing can enter. That's a white hole, a theoretical twin that only expels matter and energy. According to Einstein's equations, if black holes exist, so might white holes. They would be regions where time runs in reverse, ejecting what could never be swallowed. But unlike black holes, we've never seen one. They remain mathematical ghosts, consistent on paper, elusive in space. Some theories suggest white holes are connected to black holes, forming tunnels through space-time. Others say they're unstable, collapsing as soon as they form. Either way, they offer a strange mirror to the physics we know. People often imagine cosmic voids as pure destruction, but white holes hint at balance, exit points to black holes' entrance. So next time you think of extremes, remember, even the darkest forces may have a counterpart. Level 77. Wormholes. 2 distant points, connected by a tunnel, a shortcut through space-time. That's a wormhole, a hypothetical bridge between far-apart regions of the universe. Rooted in Einstein's equations, wormholes could theoretically link stars, galaxies, even different times, but they'd be unstable, prone to collapse, and possibly filled with exotic matter to keep them open. No evidence exists yet, just equations and dreams. Still, wormholes inspire science fiction, deep physics, and cosmic curiosity. They offer the idea that distance might not be a barrier, only a fold. People often think of space as something to travel through, but wormholes suggest something deeper. Space can bend, twist, and connect. So next time you imagine going somewhere far, ask, what if the destination was already next to you? Level 78. Event Horizon. Approach a black hole and you'll reach a boundary, a one-way surface. Not a wall, not a line, but a limit. That's the event horizon. Cross it, and escape becomes impossible. Not because of force, but because every direction, even up, now leads inward. Light can't climb out. Time itself distorts. To an outside observer, you slow, freeze, vanish. But from inside, you fall without noticing. The event horizon marks the edge between knowable and unknown. We can see material swirl around it, but what happens inside is a mystery. Not even information returns. People often think danger comes with signs, but the event horizon offers none. It looks calm until it's too late. So next time you ponder boundaries, remember, some are silent and irreversible. Level 79. Gravitational time dilation. Time doesn't tick the same everywhere. Near massive objects, it slows. That's gravitational time dilation, predicted by general relativity, confirmed by satellites and atomic clocks. The deeper you are in a gravity well near a planet, a star, or a black hole, the slower time flows. To you, it feels normal. But to someone far away, you age more slowly. Even GPS satellites account for this difference. Near a black hole, the effect becomes extreme. From afar, a falling clock seems to stop at the event horizon. But for the falling clock, time feels unchanged. Two realities, both true. People often see time as universal, but gravitational time dilation shows its relative bent by mass, warped by position. So next time you check your watch, know this: it ticks differently from the stars, and even from the mountain above. Level 80. Einstein-Rosen Bridge. In 1935, Einstein and physicist Nathan Rosen explored a strange solution in general relativity, a tunnel connecting two black holes. They called it a bridge, now known as the Einstein-Rosen Bridge. It looks like a wormhole, a folded tunnel in space-time. On one end, a black hole. On the other, maybe a white hole. The bridge connects two places, maybe even two universes, but it's unstable. It would collapse before anything could cross. Still, the math holds. and the idea lingers, inspiring scientists and storytellers alike. A portal, a passage, a fold in the fabric of everything. People often see space as distance, but the Einstein-Rosen bridge invites a different view, one where distance is optional and connection is hidden. So next time you wonder how far something really is, ask, could space itself be folding in your favor? Level 81. The Twin Paradox, Deep Dive. Two twins, one stays on Earth, the other travels through space at near light speed, then returns. When they reunite, the traveler is younger. This is the twin paradox, not a contradiction, but a revelation. It's rooted in special relativity. The traveling twin experiences time differently because of high velocity. Time dilates, clocks slow down, and while both twins think the other is moving, only the traveler accelerates, turns, and decelerates. That breaks the symmetry and explains the aging difference. The key isn't speed alone, but the full journey. Acceleration and deceleration create real, measurable differences. And every test, from particle lifetimes to satellite clocks, confirms the result. People often assume time is fair, that it treats everyone equally, but relativity says otherwise. So next time you wonder where the time went, remember, it might not be moving at the same rate for everyone. Level 82. The ladder paradox. Imagine a ladder flying at near light speed into a garage shorter than itself. To an outside observer, the ladder contracts and fits inside. But from the ladder's frame, the garage is even shorter. This is the ladder paradox. It's a thought experiment that shows how simultaneity, what happens at the same time, is relative. In one frame, the ladder fits completely inside. In another, the front exits before the back even enters. Both are correct depending on who's watching. The paradox dissolves when you realize there's no absolute timeline. Events that are simultaneous for one observer are not for another. That's not contradiction, that's relativity. People often expect space and time to behave logically, but relativity bends both, revealing truths that depend on perspective. So, next time you think two things must happen together, ask, for whom? Level 83. Zeno's paradoxes. To reach a wall, you must go halfway, then half again, then again. If you always take half steps, do you ever arrive? That's one of Zeno's paradoxes, ancient puzzles that question motion itself. Zeno argued that motion is impossible because it requires completing an infinite number of steps, and yet we walk, arrows fly, time flows. So where's the trick? The answer lies in math. We now know that an infinite series of decreasing steps can still have a finite sum. You can take infinitely many halves and still reach the end. People often confuse the infinite with the impossible, but Zeno's paradoxes remind us intuition isn't always truth. So next time something seems stuck between steps, remember, infinite doesn't mean unreachable. Level 84. The bootstrap paradox. Imagine you receive a physics book from the future. You study it, become famous, and publish the same book. Years later, someone travels back in time and gives it to you again. Where did the book come from? That's the bootstrap paradox. It's a time loop with no clear origin. Information or objects exist without a creator. They cause themselves. The effect becomes the cause, and the cause, the effect. This doesn't break physics directly, but it challenges our understanding of time, causality, and the flow of knowledge. Can something exist without a beginning? People often ask, who wrote it first? But the bootstrap paradox shows that loops can trap origin stories. So next time you find something oddly circular, ask, is this the start or the echo of something self-made? Level 85. Causality loops. Cause, then effect. That's how we expect time to behave. But in certain theories, especially involving time travel, causes and effects can circle back on themselves. These are causality loops. Imagine a person goes back in time to inspire their younger self. That younger self grows up and makes the same journey, creating a closed loop. No outside trigger, just self-contained causality, a story without a beginning. These loops don't necessarily violate physics, but they stretch logic. How do you assign blame? Credit? Where's the true origin? People often want neat timelines, first this, then that. But causality loops suggest that time may not always be linear. So next time you feel like something's coming full circle, it might be more literal than you think. Level 86. Laplace's demon. Imagine a being that knows the position and motion of every particle in the universe. With enough information, it could predict the past and future with perfect accuracy. This is Laplace's demon, a thought experiment in determinism. Pierre-Simon Laplace proposed it in the 1800s, when Newtonian physics ruled. The idea was simple. If the universe follows exact laws, then the future is fixed. Every moment, inevitable. But quantum mechanics changed the story. Uncertainty, randomness, and observation all shattered the illusion of perfect prediction. Laplace's demon can no longer see the future, not because it's blind, but because the universe is fuzzy. People often crave certainty, but physics reminds us that knowledge has limits. So next time you wonder if everything is determined, remember, even the smartest demon can't know it all. Level 87. The simulation hypothesis. What if reality isn't real? What if everything you see, the stars, the trees, your thoughts, is part of a simulation? That's the simulation hypothesis. Some philosophers and physicists suggest that if a civilization becomes advanced enough, they might run detailed simulations of entire universes. And if they can run many, then statistically, it's more likely we're inside one than the original. There's no proof, but strange clues linger: mathematical patterns in nature, quantum behavior tied to observation, limits like Planck, length, and light speed, as if we're running on code. People often laugh it off, but the question isn't just, is it true? It's, could we ever know? So next time you feel like life is surreal, you're not alone. You might just be rendered. Level 88. The Fermi paradox. Billions of stars, trillions of planets, and yet silence. That's the heart of the Fermi paradox. If intelligent life is common, where is everybody? Enrico Fermi asked this question in 1950. Since then, we've discovered thousands of exoplanets, many Earth-like. The galaxy should be teeming with signals, probes, evidence, but all we hear is quiet. Explanations vary. Maybe life is rare. Maybe intelligence is fragile. Maybe civilizations destroy themselves. Or maybe they're here, just not in ways we recognize. People often assume silence means absence, but the Fermi paradox reminds us absence of evidence is not evidence of absence. So next time you look at the stars, remember, it's not just a question of where they are. It's also why we haven't met. Level 89, Quantum Immortality. In quantum mechanics, every possible outcome happens somewhere. That's what the many worlds interpretation says. And from it comes something eerie, quantum immortality. Imagine a scenario where you could die. In some universes, you do. In others, you survive. But from your perspective, you only ever experience survival. No matter how unlikely, there's always a version where you continue. Over time, your consciousness follows only the paths where you remain alive, even if barely. This leads to the idea that you might never experience death, just increasingly improbable survival. It's not mainstream science, but it raises deep questions about identity, perception, and what it means to end. So, next time you wonder about fate, consider this. Maybe your awareness can't witness its own absence. Level 90. The anthropic principle. Why does the universe allow life at all? Why do physical constants seem perfectly tuned? That's the question behind the anthropic principle. It says, the universe appears fine-tuned for life, because if it weren't, we wouldn't be here to observe it. That's not an explanation, but a filter. We exist in a universe that permits observers because we're observers. Some see this as trivial, others see it as profound. It plays a key role in multiverse theories, suggesting countless other universes may exist, most lifeless, some not. People often ask why the universe feels made for us. The anthropic principle replies, maybe it's not about being made for us, but about only seeing where we can survive. So next time life feels unlikely, remember, it had to be, or you wouldn't be asking. Level 91. The measurement problem. In quantum mechanics, particles exist in many states at once until you measure them. Then suddenly, one outcome appears. That mystery is called the measurement problem. The wave function describes probabilities. It's smooth, continuous, and unrealized until observed. But what exactly causes collapse? Is it the act of measurement? The presence of consciousness? A hidden variable? No one knows. Different interpretations try to explain it. Copenhagen, many worlds, decoherence. But at its heart, the measurement problem reveals a gap between the math and the moment something becomes real. People often trust in observation. Seeing is believing, but quantum physics asks the opposite. Is believing what makes it seen? Level 92. The problem of free will. If the universe follows strict physical laws, are your choices really yours? That's the problem of free will, a tension between physics and personal experience. Classical physics is deterministic. Every event follows from the one before. Quantum physics adds randomness, but randomness isn't freedom. So where does choice come in? Some argue consciousness brings unpredictability. Others say free will is an illusion, a useful story we tell ourselves. And yet, you feel like you choose. That experience persists. People want control, meaning, agency, but the universe may not owe us that. So next time you face a decision, remember, even if your path is uncertain, it's still yours to walk. Level 93. The nature of consciousness. You're aware, you think, feel, imagine, but what is consciousness? Where does it come from? That's one of the deepest questions in science and philosophy. Some theories say it arises from brain complexity neurons firing in patterns. Others suggest it's more fundamental, like a property of the universe itself. But no one knows how subjective experience your sense of being emerges from matter. This is the hard problem of consciousness. Not how the brain reacts, but how it feels to be you. Why is it like anything at all? People live their whole lives inside their minds, but no one has ever held a thought in their hand. So next time you wonder what's real, remember, awareness itself may be the strangest phenomenon of all. Level 94. Is math discovered or invented? Is math something we create or something we find? When we write equations, are we building a language or revealing hidden truths? Platonists say math exists timeless, perfect, waiting to be uncovered. Others argue it's a human tool shaped by our needs, culture, and perception. Both views have merit, and both raise deeper questions. Why does math describe the universe so well? From galaxies to atoms, its rules hold. Is that coincidence or connection? People often see math as cold or rigid, but it's also profound, bridging logic and mystery. So next time you solve a problem or draw a curve, ask, did I make this or did I meet it? Level 95. The information paradox. Drop something into a black hole and it's gone. Not just matter, but information. That's the information paradox, a conflict between quantum mechanics and general relativity. Quantum theory says information is never truly lost, but black holes seem to erase it. When they evaporate through Hawking radiation, the particles they emit carry no trace of what fell in. That violates one of quantum's core principles. Physicists have proposed solutions. Maybe information escapes in subtle ways, or stays imprinted on the event horizon. Maybe black holes don't fully vanish. Maybe reality itself needs new rules. People often think of black holes as endpoints, but the information paradox shows they might be puzzles, places where our best theories clash. So next time you imagine something disappearing forever, remember, the universe may be better at remembering than we think. Level 96. What is a law of nature? We say things fall because of gravity. Light bends because of curvature. Particles behave according to quantum rules. But what exactly is a law of nature? Is it a description, a summary of behavior, or something deeper, something the universe must obey? Some see laws as patterns we've observed. Others believe they are woven into reality, guiding every interaction without exception. But where do they come from? Why do the laws have the form they do, not simpler, not more chaotic? Why can they be written as equations at all? People often speak of laws as fixed and eternal, but perhaps they emerge, shaped by symmetry, necessity, or deeper truths still unknown. So next time you hear, "It's just physics," pause. You're not just seeing rules, you're glimpsing the order, behind existence. Level 97. The boundary of nothingness. What lies beyond the universe? If space is expanding, what's it expanding into? And if time began, what was before? These questions lead to the boundary of nothingness. But nothingness isn't empty space. It's the absence of space, time, matter, even the laws themselves. No distances, no durations, no definitions. Just not. Can such a state exist? Physicists and philosophers debate it. Some say the universe emerged from quantum fluctuations in a vacuum, but even that vacuum had rules. So what came before rules? People often picture nothingness as dark or blank, but real nothingness may be beyond imagination, not void, but absence of any possibility. So next time you think of nothing, remember, you might already be thinking of something. Level 98. The end of infinity. Infinity seems endless, more than any number, larger than all limits. But can it end? Can something so vast actually break? In some theories, infinity is real, the number of stars, the size of space, the possibilities of time. In others, it's a symbol, a mathematical tool, not a physical thing. Even space itself might be finite, yet unbounded. Black holes, quantum loops, and the edge of space-time may all challenge the idea of infinity, not with walls, but with constraints. Not with stop, but with folds. People often use infinite to mean unknowable, but the end of infinity might be a beginning, the point where language breaks and wonder begins. So next time you say, forever, ask yourself, does it truly stretch or simply loop? Level 99. Why anything exists at all? Of all the questions, this might be the deepest. Why is there something instead of nothing? Why should existence happen at all? Physics can describe how the universe behaves. Cosmology explores how it may have begun. But the question of why there is anything in the first place, not just empty silence, remains unsolved. Some propose necessity, that reality must exist in some form. Others say it's pure chance or a brute fact without explanation. Religious views offer purpose. Scientific ones offer structure. But no answer silences the question entirely. People live surrounded by things, stars, thoughts, each other. But the presence of something, instead of the absence of everything, may be the greatest mystery. So next time you pause in silence, feel the ground, breathe the air, know this: you're part of the answer to a question no one fully understands. Level 100. The ultimate paradox, you. After all the laws and particles, after space-time, entropy, and equations, there's one question left. You, the observer, the experiencer, the paradox that asks, and here's the answer. You are made of atoms, following physics like everything else. But you also wonder, you dream, you ask questions about the very system you're part of. That's more than biology, it's reflection. Some say consciousness is just computation. Others see it as a doorway to something more. But either way, you are a universe, observing itself. A mind shaped by matter, asking why it matters. People chase the mysteries out there, but the most persistent one may be within. So as you rest tonight, remember, of all the paradoxes we've explored, the one still unfolding is You